All right, in our last video for this chapter, we're going to talk about electric fields. And as we've been doing with the last couple of chapters, I will open a surprise blind bag at the end. This one's going to be from Toy Story 4, so we'll cross our fingers to get a Forky. We'll see what happens. But anyway, electric fields. Electric fields are another way of interpreting electric charge and another way of approaching problems that deal with electric charge. And we're not going to get into the details, but I want you guys to have a general picture of how these things look. So in general, excess charge creates electric fields. So when you've got some leftover positive charge, some leftover negative charge, whatever it may be, it's going to create an electric field. And the way these fields interact recreates the effects we've talked about. The like charges repelling, the opposite charges attracting. The field lines are another way to interpret that. Now when drawing field lines, the electric field lines always point from positive to negative. And so we'll start off by just looking at a couple of basic examples. If we had some leftover positive charge, you have field lines pointing outwards from that positive charge. Similarly, if you had some leftover negative charge, you have field lines pointing inwards to that negative charge. Now where things get interesting is when we've got multiple charges floating around. When you have multiple charges floating around, things get a little more complicated, but the same sort of rules apply. So say we had a situation like this with a positive charge and a negative charge. Well, you still have field lines leaving the positive charge, but they are drawn toward that negative charge. So the field lines go straight from the positive to the negative along that line, or they might kind of curve and bend towards the negative charge. And on this opposite side, they go straight away from the positive charge, straight towards the negative charge. And we can see the way that opposites attract in the field line patterns themselves. It's almost like these things are being pulled together. Well, the other situation is two similar charges or two like charges. Here I drew two positive charges. Well, the field lines want to go away from the positive charges, so they start out leaving the proton, but if this were to head straight over, it starts going towards another proton. We shouldn't have field lines pointing towards a positive charge. We need them to point away, so they go outwards and then they bend away because they don't want to point at the positive charge. They would only want to point at negative charge. So when you have two positive charges nearby, those field lines come out and then push away from each other. And you can see in this diagram the field lines pushing each other away. And this is another interpretation of why like charges repel and why opposite charges attract. If we were to just take another charge and sort of drop it into an electric field, a positive charge in an electric field is pushed in the direction of the field, and negative charges are pushed in the opposite direction of the field. If you can imagine, if we dropped a positive charge right here, it gets pushed away from the positive towards the negative. Or if instead we dropped a negative charge, it would go towards the positive, away from the negative, going opposite the field line, or the direction of the field line. And this is quantified in this equation here, that the force, the electric force, is the amount of charge times the field that it's in. That E, F equals QE, is the equation. That E is the electric field strength. And if we wanted to look at the units of electric field strength, it's given in newtons per coulomb. How much force gets put on how much charge? Depending on how much charge you have, that determines how much force there is. The other thing is the field strength itself. So a big charge gets pushed harder, a small charge gets pushed less. And of course, a stronger field is going to give a stronger push than a weaker field. And this is very similar, it turns out, to mass in a gravitational field. So just like an object with mass feels a force in the presence of a gravitational field, an object with charge feels a force in the presence of an electric field. Now, if you were to look up at this negative charge electric field diagram, imagine if instead this was just the planet. Well, we can ignore that minus sign for a second. We actually have gravitational field lines pointing downwards all over the planet. And if you put a mass in it, it gets pulled along that field line. It's the same idea. An object with mass feels a force in the presence of an electric field. An object with charge feels a force in the presence of an electric field. Did I say that backwards? Mass feels force in a gravitational field. Charge feels force in an electric field. And just like we had F equals QE for electric field, or not as we see that F equals QE for an electric field, we had that F equaled mg in that gravitational field. The G is the field. You put a mass in it, it feels a force. The E is the field. You put a Q in it, a charge, it feels a force. So that is just a brief exposure to electric fields. Again, I'm not going to have you guys use any equations from this chapter, but I want you to understand and be able to picture what's going on when we have discussions about charge. So that sums it up for chapter 10. Let's go ahead and crack this Toy Story 4 mini. Come on, Forky. Everybody loves Forky. Oh, it's one of my other favorites. It's not Forky. It is Duke Kaboom, voiced by none other than Keanu Reeves, the one. All right, folks. Well, that concludes it for Chapter 10. I will see you guys next week for Chapter 11. We will study circuits, or as I like to call them, the Sudoku puzzles of physics. I think even those of you who are not fans of math will enjoy solving some circuits. They're very straightforward. They follow a pattern, and it honestly is fun. There's no other way to put it. I know I'm probably sound crazy, but trust me, circuits are going to be fun. All right, see you guys next week.